Welcome to my projectbazaar.com.
Next, we discuss about the product for improved 8-point approximate DCT for image and video compression requiring only 14 additions. Next, we see the abstract for the product. Reasons here have experienced a significant demand for high dynamic range system that operate the high resolutions in a particular high quality digital video in multimedia devices and video over internet protocol networks are prominent areas where such requirement are evident. Other noticeable field of geometrical remote sensing and traffic cameras and automatic surveillance cameras, security cameras, etc. in used in the wireless sensor networks. Video processing systems such as the HEVC requiring low energy consumption needed a multimedia market has led to extensive development in fast algorithm for the efficient approximate of 2D DCT transforms. The DCT is employed in a multimedia of compression standards due to its remarkable energy computation properties. Multiplayer free approximate DCT transforms have been proposed that offer superior compression performance at very low circuit complexity. Such approximations can be realized in digital VLSI hardware using addition and subtraction, only leading a significant reduction in chip area and power consumption compared to the conventional DCT and integer transform. Then the transform DCT architecture compared to previous methodologies. In this paper, we introduce a novel 8-point DCT that requires only 14 addition for the DCT process. This proposed transform process low computational complexity and to compare to the state of art of DCT approximate in terms of both algorithm complexity for the peak signal to noise ratio process. The proposed DCT architecture process we candidate for the reconfigure video standards such as the HEVC applications. Our proposed DCT architecture we designed for the VHDL language. Then we develop the Xilinx 14.2 software for the required 14 addition based DCT architecture. Next, we see the flow diagram for the product. First, we design the overall DCT architecture. This architecture consists the adder section for our required first and second stage and third stage process. Each stage for the addition process 8-bit and 9-bit and 10-bit addition to apply the CSI unit architecture for our the required overall DCT architecture. The CSI architecture used to carry propagation time and to reduce the carry propagation delay for our overall architecture process. Thus, the input integer bits are converted to the binary process. Thus, the binary bits are applied to the first stage adder section. This adder section to apply the CSI unit addition architecture process. Then to results for the CSI addition architecture results and to apply the D flip-flop registers section. These sections mainly used to the store the results for 8-bit addition results and to combine with sum and carry bits also. These register elements based on our clocking section. This clock to control the storage results and the clock activation to apply the another process for the storage unit architecture. Then the second and third stage process same as to the first stage process. Each addition section, thus the section to apply the CSI unit, then to apply the register element, and the third process to apply the 9-bit results, then to addition the CSI unit addition process, then to apply the register element architecture process, and to apply the final transform results for acute DCT architecture. This overall architecture used to only 14 addition process in our first and second third stage process our overall DCT architecture. Thus the storage element mainly used for D flip-flop register elements. These are the blocks are applied to the overall DCT architecture results. And finally we see the output for the product. First we open the fixed DCT Xilinx ISC project. Then to run the fixed TCT Xilinx ISC project. Our project was developed in VHDL programming. Then to apply the structural designs modeling for our the CSA and D flip-flop architecture results. Then to select the simulation process and just to double click the simulate behavioral model. Then to open the Xilinx ISC sim project. This simulation process only developed for the Xilinx ISM project list. Then to apply the clocking signal for our architecture process. Then to apply the 8-point input for our the binary required binary results. This the binary result to apply the each or every architecture process. This 8-point DCT to record the only 14 addition results are applied to the process. The applied result are applied for the required binary results. Every input to apply the 8-bit binary result. This binary result based on the separate integer value. Then to run the time specified on the toolbar and to apply the clocking signal. Then to display the final output result for our overall architecture results. Then to close the simulation result and to calculate the implementation process. The implementation process to see the view RTL schematic process. This process to run the RTL diagram for overall DCT 8-point DCT architecture. The 8-point DCT architecture only used for 14 addition process. Each and every module consists the overall architecture process. Then to apply the technological diagram. The RTL diagram will represent the what are the logical blocks placed in our architecture. The technology diagram will represent the what are the lookup tables and input or output, bounded input outputs, then the while length and the flip-flop pairs placed in our DCT architecture. Then to go the design summary process. The design summary process to calculate the synthesis report for required DCT architecture results. This device utilization summary mainly considers for the overall slices LUT and flip-flop pairs, then bounded input outputs. These results mainly used for area of overall architecture process. Then the timing summary to calculate the path delay time for 5.192 nanoseconds for overall DCT architecture. For our CSA based DCT architecture results.